Introduction to Work-Energy Theorem for a Variable Force. Hello guys. Good to see you all. In our daily life, we come across many situations, from which we can say that, work is done by force. Performing work requires a lot of energy. For example, we can say that, a man is doing work on the car, by applying some force. Here, the force acting on an object, equals the change in the kinetic energy of the object. This is known as the work-energy theorem. In nature, the work done by the forces is of two types, constant force, and variable force. In that, if magnitude as well as the direction of the force remains constant, then we can say that, force is of constant nature. If either magnitude, direction or both changes, then we can say that, force is of variable nature. In this video, we will learn more about the work-energy theorem for a variable force. Therefore, at the end of this lesson, you will be able to explain the work-energy theorem for a variable force, and solve problems based on work-energy theorem for a variable force. Work-energy theorem for a variable force. The work-energy theorem states that, the work done by the net force acting on a body is equal to, the change produced in the kinetic energy of the body. Let F be the variable force. Then, work done by a varying force, W is equal to, integral F dx, in the limits xi to xf. Where xi is the initial position of the body, and xf is the final position of the body. If the velocity of the object at an instant is v, then its kinetic energy at the instant is expressed as shown on the screen, where v is the velocity of the object. Differentiating equation 3 with respect to time t, we get the rate of change of kinetic energy, as shown on the screen. Thus on simplification, we get the equation as shown. On further simplification, we get dke divided by dt is equal to mdv by dt into v. On the right side of the equation, we know that dv by dt is the ratio of change of velocity, which is the acceleration of the body a. Thus we get dke by dt is equal to mav. However, according to Newton's second law, F is equal to ma. That is, mdv by dt is equal to F. Therefore dke by dt is equal to Fv. Also the velocity term v in the expression can be represented as the rate of displacement, v is equal to dx by dt. After simplification, we get equation 4, as shown on the screen. Now integrating equation 4 in the limits from xi to xf for the displacement, and for ki to kf for the corresponding kinetic energy, we get equation 5 as shown. The left side of the equation indicates the change in kinetic energy, and the right side of the equation indicates the work done on the body by the variable force. Thus, we see that the work done by a variable force on a body is equal to the change in kinetic energy of the body. Thus, the work-energy theorem is proved for a variable force. While the work-energy theorem is helpful in a variety of problems, it does not, in general, incorporate the complete dynamical information of Newton's second law. It is an integral form of Newton's second law. And this law is a relation between acceleration and force at any instant of time. Another observation is that, Newton's second law for 2 or 3 dimensions is in vector form, whereas, the work-energy theorem is in scalar form. In the scalar form, information with respect to directions, contained in Newton's second law is not present. Well, guys, now let's discuss problems based on the work-energy theorem for a variable force. A block of mass m is equal to 1 kg, moving on a horizontal surface with speed vi is equal to 2 meters per second enters a rough patch ranging from x is equal to 0.1 meter to 2.01 meter. The retarding force Fr on the block in this range is inversely proportional to x over this range, as shown on the screen, where k is equal to 0.5 joules. What is the final kinetic energy and speed Vf of the block as it crosses this patch? Coming to the solution, according to the work-energy theorem, work done by all the forces is equal to the total change in kinetic energy. That is, W is equal to delta KE. Then the variable force equation of the work-energy theorem is given as shown. Then the given retarding force Fr is equal to minus K by X, hence, we get the equation as shown. Now by substituting the K, V, I and X values, we get the simplified equation as shown on screen. Then on further simplification of the equation, yields the equation as shown. Using the integral of 1 by x is equal to, log E of x, is equal to, ln x formula, we get the simplified equation as shown. After simplification, we use log A minus log B, is equal to, log A by B formula. Then on further simplification, we get Vf square is equal to 1. From this, we get the final speed of the block Vf, is equal to, 1 meter per second. Then the final kinetic energy is calculated, using the formula shown. Finally by substituting the mass m, and final speed of the block value Vf, we get the final kinetic energy as 0.5 joules. Conclusion. Thus, we can conclude that, based on the variable force, we derived the work-energy theorem. From this, we learnt that, the work done on an object, is equal to, the change in its kinetic energy. Also, a constant force is rare in the everyday world. Hence, variable force is what we encounter in our daily life. Summary. This brings us to the end of the lesson. In this lesson, you have learnt that, work done by the net force acting on a body, is equal to the change produced in the kinetic energy of the body. This is known as the work-energy theorem. Then we derived the expression of the work-energy theorem, for a variable force. And finally solved a problem, based on the work-energy theorem for a variable force. So, that's all for today's session. Bye, guys. Catch you in another interesting video.